And 11.8, we're running through power series. We're still working up to evaluating functions that we don't know how to take an antiderivative for, to integrating some functions that maybe don't have nice elementary antiderivatives with series. And we've got a couple more sections where we'll look at some different types of series we can use to integrate or take derivatives of some functions that maybe we couldn't without them. But right now we're just doing power series and we're still just worried about where they converge. So we've got a definition and some things I'll read through before we try some problems, so you don't have to watch me write it all out, but bear with me as we read. So definition: if x is a variable and the c sub n's are coefficients, then an infinite series of the form summation n equals 0 to infinity c sub n times x to the n, which would be the sum of c sub 0 plus c sub 1x plus c sub 2x squared, all the way up to, right, all these things of the form c sub n x to the n, is called a power series. So just a variable to a power, right? That's what makes it the power series. A series of the form n equals 0 to infinity c sub n times the quantity x minus a to the n, or expanded c sub 0 plus c sub 1 times the quantity x minus a plus c sub 2 times the quantity x minus a squared, all the way up, is called a power series centered at a. So we've got some examples just to see some centered at different places. Summation from n equals 0 to infinity of x to the n over n factorial, which would be expanded as a 1 plus x, right? X over 1 factorial is just 1. 0 factorial, remember, is defined to just be 1. And x to the 0 would be 1, so 1 for the first term. Plus x over 1 factorial, or just x, plus x squared over 2 factorial, plus x cubed over 3 factorial, plus more terms, is a power series centered at 0. Right, you could write it as x minus 0 to the n if you want. And then for b, we've got the summation n equals 0 to infinity of minus 1 to the n times the quantity x plus 1 to the n, or expanded 1 minus quantity x plus 1 plus x plus 1 quantity squared minus x plus 1 quantity cubed, on and on and on, is a power series centered at negative 1. And for c, we've got summation n equals 1 to infinity of 1 over n times the quantity x minus 1 to the n equals expanded as x minus 1 plus 1/2 times the quantity x minus 1 squared plus 1/3 times quantity x minus 1 cubed. All right, is a power series centered at 1. And so you can find the centers. You can see them that x plus 1 to the n we can write out as an x minus negative 1 to the n. The x minus 1 to the n, pretty self-explanatory. But we can see that a, right, that value we're subtracting off, same as we did for centers or vertexes for circles, parabolas, things like that in the past. All right, so what we're worried about is finding out where these things converge, and we can talk about a radius of convergence and an interval of convergence. So we've got a note here: the sum of the series is a function, right? F of x equals c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a quantity squared, on and on and on, whose domain is the set of all x for which the series converges. If x equals a, we get f of a equals our summation from 0 to infinity c sub n times a minus a to the n, right? That a minus a would give us a 0, which would give us just a sub 0, right? That first coefficient times 1. Or you could put c sub 0 if you want there. Right, and so just c sub 0, everything else is going to go away. And 0 to the 0, they say, is 1 here. So we've got just that early coefficient, but we get a sum, right? We can evaluate it, everything else goes to 0. So the power series is always going to be convergent at its center. They can also be convergent in an interval centered at a, right? The a, again, being the center. And we're going to use the ratio test to determine the convergence for the series. All right, the theorem gives us our three possibilities. For a given power series, summation n equals 0 to infinity of c sub n times quantity x minus a to the n, there are only three possibilities. Either the series converges only when x equals a, so only at its center. The series converges for all x, in which case we'd say the radius is infinite. And there's a positive number r, such that the series converges if absolute value of x minus a is less than capital R, and diverges if absolute x minus a is greater than capital R. So we've got r here, that capital R is the radius of convergence. If the series converges only at x equals a, then the radius of convergence is r equals 0. Right? We can't expand in either direction from the center, so the radius is 0, and we just have that one value a where we converge. If the series converges for all x, then the radius of convergence is capital R equals infinity. Right? So we can expand forever in both directions. Our radius is infinite. We converge for all x. And the set of all values of x for which the power series converges is what we call the interval of convergence of the power series. So we'll do a few examples together, hopefully to get that straight. And it's just ratio tests, so you should be pretty good with it after prepping for the test and trying it in the last full section we did. But let's do some. All right, so we're going to find the radius of convergence for the following power series. For a, we've got the summation from n equals 0 to infinity of n factorial times x to the n. We can think of it as x minus 0 to the n again, or again, say that we are centered at 0. Right? And to find the radius of convergence, we're using the ratio test. So we've got the limit as n approaches infinity of a sub n plus 1 over a sub n, which here would be our limit as n approaches infinity, absolute value n plus 1 factorial times x to the n plus 1, all over n factorial times x to the n. We can write that out to see our cancellations or our division. Limit as n approaches infinity. The n plus 1 factorial we can think of as an n plus 1 times n factorial. And the x to the n plus 1 we can write out as x to the n times x. In our denominator, we've just got the n factorial and x to the n, so both of those are going to cancel out with the factors in the numerator. And we'll be left with here the limit as n approaches infinity of absolute n plus 1 times x. That absolute value of x we can pull outside the limit. It does not depend on n, so it's not going to change as n goes to infinity. And we're left with inside the limit now that absolute value of n plus 1, which is going to go off to infinity as n approaches infinity. And so since our limit here would be infinity, we diverge for all, let's put it this way, absolute x greater than 0, and which would mean our radius of convergence is 0, right? So we're not expanding in either direction. There's no other values that work, but we always converge at the center. And so we won't usually show it, but we could write it out once just to see it. If x equals 0, we got our summation here of n equals 0 to the infinity of n factorial times 0 to the n. And so they gave you that first term above. We'd have 0 factorial times 0 to the 0. Both of those defined to be 1. Oops, but let me do some more first. Plus, we'd get a 1 factorial times 0 to the first, plus 2 factorial times 0 squared. Right, so all those other terms are 0, but the first one would just be 1. So we converge here, we get a sum, which means we're convergent at the center, which was in the little note above. But no other values work, so our radius of convergence is 0, right? It's just the center. For b, we've got our summation from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1, all divided by quantity 2n plus 1 factorial. So again, we're centered at 0. We've got just an x there. And we'll see that as we look at the radius after. But we've got our limit as n approaches infinity. Ratio test again, a sub n plus 1 over a sub n would give us our limit as n approaches infinity of an x to the 2 times n plus 1 over a 2 times n plus 1 factorial. And I'll just multiply by the reciprocal here. So our a sub n term, we'd get a 2n plus 1 factorial after the division in the numerator over an x to the 2n plus 1. And so we can write out for this limit as n approaches infinity, expanded inside to help us simplify, and x to the 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial over x to the 2n plus 1. And so expanding the factorial like we've done in the past and looking at what happens with those x's, we get an x to the 2n times x cubed times that 2n plus 1 factorial for our numerator. And in our denominator, we can get a 2n plus 3 times 2n plus 2 times 2n plus 1 factorial times an x to the 2n times x, right, for that extra 1 down there. So the x to the 2n's are going to divide out. The 2n plus 1 factorials will divide out or check out. And then we've got some simplification. We've got our limit as x approaches infinity of an absolute value. The x cubed over x would leave us with an x squared in the numerator. Our denominator, we'd have a 2n plus 3 times quantity 2n plus 2, which you could multiply out but don't need to. We can pull that x squared outside of our limit. Don't need the absolute values because it's x squared, but I already wrote them, so I'll leave them. I wrote one in there, but limit as n approaches infinity of, we'd have a 1 over 2n plus 3 times 2n plus 2. Right, as n goes to infinity, that thing's going to approach 0. So an x squared, some positive quantity times 0 is always going to be 0. So we have less than 1 there, right, for all x. Which means we converge for all values of x, and our radius then would be infinity. All right, for C, we've got our summation n equals 0 to infinity of 3 times quantity x minus 2 to the n. So you can see different center here. We're centered at x equals 2. And if we take our limit to find out where we're convergent, we've got our limit as n approaches infinity, a sub n plus 1 over a sub n. We could write that out as the limit as n approaches infinity. We've got a 3 times x minus 2 to the n plus 1 over 3 times x minus 2 to the n. That would leave us just with a limit as n approaches infinity of absolute x minus 2. Right, the n plus 1 would give us n plus an extra x minus 2 factor. The 3's divide out, so we've got just a factor of x minus 2 left. It's not affected by n going to infinity, so this is just the absolute value of x minus 2. According to the ratio test again, we converge if this thing is less than 1, which means we'd get an inequality of -1 less than x minus 2 less than 1. And then if we add 2 everywhere, right, to solve that inequality, we end up with a 1 less than x less than 3, or x is between 1 and 3. Now our radius of convergence comes from that 1 that we're less than, so our r here equals 1. You can also see it looking at that interval from 1 to 3, right? Our center is at 2, so we're going 1 in each direction, right, to get our interval of convergence around that center with radius 1. But r is just 1 here, and so what we do want to look at as we continue here with C is finding the interval of convergence then. So we're saying that this converges for x between 1 and 3, but we don't know what happens at the endpoints. So ratio tests can't be used to check for convergence at the endpoints, so we need to revert to previous methods. If you did plug in 1 or 3 to that inequality above, right, the absolute value of x minus 2 less than 1, you'd end up with 1 each time. And 1, remember, was inconclusive for the ratio test, so we need to look at other methods. And so to do that, we're just plugging in 1 and 3 into our original series and seeing what happens. So for x equal to 1, we've got our summation, n equals 0 to infinity. We'd have a 3 times 1 minus 2 to the n, or summation n equals 0 to infinity of a 3 times -1 to the n. Our limit there, right, the 3 doesn't even matter. It's a constant. We could pull it out front, but our limit as n approaches infinity of minus 1 to the n does not exist. It's going to bounce around. So we are divergent when x equals 1. And if x equals 3 here, we get our summation from 0 to infinity of 3 times 3 minus 2 to the n, or summation here of n equals 0 to infinity of 3 times 1 to the n, or just 3, right? The 1 to the n is always going to be 1. But our limit there, right, n to infinity of 3 is just 3. That's not 0, so we are divergent when x equals 3. Right, so just test for divergence. We didn't get a limit of 0 for either, so we're not convergent at either endpoint. So our whole interval of convergence, I keep writing IOC, is just 1, 2, 3, right? Open endpoints, neither is included. And our radius of convergence again was 1. All right, so a few more. Let's find the whole interval of convergence for the following power series. All right, we start exactly the way as we did just finding the radius. We're going to find the interval of convergence for the following power series. For A, we've got the summation from n equals 0 to infinity of x to the n over n. So to find the radius of convergence, or the inequality we need for the interval, we're using the ratio test. We've got our limit as n approaches infinity of absolute a sub n plus 1 over a sub n. Which would give us our limit as n approaches infinity of x to the n plus 1 over n plus 1 times, right, our reciprocal for a sub n would just give us an n over x to the n. And when we simplify, we get our limit as n approaches infinity. We'd have an x times n in the numerator, right, that 1 extra x over n plus 1. We can pull the absolute x out, and not affected by the limit as n goes to infinity again. So we'd have absolute x times the limit as n approaches infinity of n over n plus 1. You could again write out where we divided everything by n, or do L'Hopital's once, but our limit for that is just going to be 1. So we end up with just absolute x. To be convergent, we need that to be less than 1. So we get an inequality -1 less than x less than 1. Our radius of convergence is 1. Again, we didn't write it, but we could see this whole thing is centered at 0. Right, we've got radius 1 here. And we want to worry about the endpoints. So if x equals -1, we get a series of the form n equals 0 to infinity, -1 to the n over n. That's our alternating harmonic series. So you could write out some more if you need to, but this is convergent. Right, our alternating harmonic series. We've done it a few times, but you can confirm it's decreasing, right? 1 over n plus 1 is less than 1 over n, and the limit as n goes to infinity of 1 over n is 0. So we are convergent when x equals -1. But if x equals 1, we get a series of the form sum n equals 0 to infinity of just a 1 to the n over n, which is our harmonic series, right? This would just be our series, n equals 0 to infinity, 1 to any power is just 1, 1 over n is our harmonic series, so it's divergent. We can say divergent harmonic series, which gives us an interval of convergence then of bracket -1 to parenthetic 1. All right, so we converge at the endpoint -1, and then from everything from there up to, but not including the other endpoint at 1. All right, for B, we've got the sum from n equals 0 to infinity of a -1 to the n times quantity x plus 1 to the n all over 2 to the n. So we are centered here at -1. And we're going to take our limit with our ratio test to find out where we converge. So our limit as n approaches infinity, a to the n plus 1 over a to the n. would give us a limit as n approaches infinity, absolute. Don't need the -1 to the n's anymore, so we'd get an x plus 1 to the n plus 1 over 2 to the n plus 1. Dividing would give us times our reciprocal, so 2 to the n over x plus 1 to the n. And we can simplify all that. We'd get our limit as n approaches infinity. In our numerator, we'll be left with just the 1 extra x plus 1 factor. In our denominator, the extra 2. And that doesn't depend on n at all, so we get an absolute value of x plus 1 over 2 as our limit. We're convergent if that thing is less than 1. If we manipulate algebraically, we would get the absolute value of x plus 1 then needs to be less than 2. That 2 being our radius of convergence. And if we expand to get rid of the absolute value, we'd have -2 less than x plus 1 less than 2. If I subtract the 1 everywhere to solve for x, I find that x is between -3 and 1. So we've got our interval, but we need to check the endpoints. You can see the center at -1. If I add 2, I get to 1. Subtract 2, I get to -3. So my interval lines up with the radius. And now we've got to check the endpoints. So if x equals -3, we end up with our summation from n equals 0 to infinity, -1 to the n times -3 plus 1 to the n over 2 to the n, which would give us a summation from 0 to infinity of a -1 to the n times a -2 to the n over 2 to the n. And this, if we simplify further, I'll try and write out some more steps. Our summation, n equals 0 to infinity. We could think of a -1 to the n times a -1 to the n times 2 to the n to break apart that -2 all over 2 to the n. The 2 to the n's would divide out. -1 to the 2n is just a 1. So really our summation boils down to summation from n equals 0 to the infinity of 1, which is divergent. Right? We just keep adding 1 over and over and over again, so our limit would be infinite. And if x equals +1, we get something of the form summation n equals 0 to the infinity, -1 to the n of 1 plus 1 to the n over 2 to the n. Or our summation n equals 0 to the infinity, -1 to the n times 2 to the n over 2 to the n. Again, the 2 to the n's cancel out. We've got our summation n equals 0 to infinity of -1 to the n. That doesn't have a limit, so it's divergent. So we are not convergent at either endpoint, which means our whole interval of convergence is just the -3 to 1, right? Not inclusive, so neither endpoint. And last one here, we've got the summation from n equals 0 to infinity of x to the n over n squared. So the x to the n is centered at 0. All right, if we look at the limit to find out where we're convergent, we've got the limit as n approaches infinity with that ratio test, a sub n plus 1 over a sub n, which gives us our limit as n approaches infinity of x to the n plus 1 over n plus 1 quantity squared times reciprocal of the original, n squared over x to the n. Will give us the limit as n approaches infinity of n x times n squared over n plus 1 squared, right, all in absolute. And then we can take our absolute x out. It's not affected by the limit. We'd still have our limit as n approaches infinity of n squared over, we can write it out, n squared plus 2n plus 1. Dividing everything by n squared, using L'Hopital's twice, or recognizing that we've got the same power, would give us a limit of 1 there again. So we end up with just absolute x. So convergent again by ratio test if this thing is less than 1. And so expanding, that absolute value, we'd find -1 less than x less than 1. So our radius of convergence, again right here, r equals 1. And we want to check our endpoints, -1 and 1. So if x equals -1, we end up with the summation n equals 0 to infinity of -1 to the n over n squared. This is alternating, hopefully recognize it as convergent, but we can look at some things. So 1 over n plus 1 squared is less than 1 over n squared. And our limit as n approaches infinity of 1 over n squared equals 0, right? So it converges by the alternating series test. And if x equals +1, our summation is from n to infinity. We'd end up just with 1 to the n over n squared, or summation n equals 0 to the infinity of 1 over n squared. And this is a convergent p-series, right? Our p equals 2, greater than 1. So we are convergent at both endpoints, which makes our interval of convergence a bracket -1 to 1 bracket. All right, so ratio test is kind of the whole section. We are looking for a radius of convergence or interval of convergence. The ratio test is inconclusive when x equals 1, so we've got to use other methods to check the endpoints. Most of the time it should boil down to something you're pretty familiar with, p-series, alternating series, things like that. But try some of these, and then we'll look at putting other functions into the form of power series in the next section.